curves that we cannot do with sharp points. One of those things is that we can always, if we have a curve, no matter how kind of sharp that curve is, but it's a curve, we can always draw a line that is tangent to that curve at any point on the curve. I have this green line drawn that's tangent to my blue curve, and it's tangent at this point. But no matter what point I picked, if I pick a point over here, I can draw a line that's tangent to my curve over here. If I pick a point over here, I can draw a line that's tangent to my curve over there. It doesn't matter what point I pick. If I have a sharp point on my graph, then at that point, I can't draw a tangent. You can draw, but they're not really tangent, but I understand what you're saying. And yes, you can draw a lot of lines that are kind of the same relationship to this curve, to this graph. But I also want you to recognize that one of the nice things about lines is that lines have these descriptors that we can always come back to. One of them is the slope, right? It's more so than other things that we graph. Lines we can describe through various things, the slope being one, and I want you to think about, and I think probably it's been described this way to you, the slope is a rate of change, right? Has it ever been told to you in those terms? Yeah. That the slope is the rate of change, the rise over the run. Yeah. Now, it's a little bit, it's natural for us to think about this green line as having a rate of change. That's very natural for us to think about. But we also want to think about the blue graph having a rate of change as well. And that the rate of change of the blue graph is constantly changing. The green graph, the rate of change is constant. The blue graph, when I'm up here, its rate of change is very largely negative, right? And as I come down my graph, the rate of change is still negative, still getting smaller, but at a less fast pace, and less fast, and then somewhere down here, not too far from my point that I've used, somewhere down here, the rate of change is 0. It's not decreasing and it's not increasing. And then it starts to increase. My rate of change becomes positive. And it starts at a very small positive number, and it gets to be a bigger and bigger and bigger positive number as it starts to increase at a faster rate. So what we're going to do is we want to be able to quantify the rate of change at any place on this graph, just like we can with lines. So here's what we're going to do. We're going to define the rate of change of any place on this graph. We are going to define the rate of change to be the rate of change of the line that is tangent to this graph at this point. When I'm over here and I draw my tangent line and I find the slope of my tangent line, that's the rate of change of this point of my graph. And I'm down here and I draw my tangent line, find the slope of my tangent line, that's the rate of change of this point in the graph. And when I'm right here where I've marked and I draw my tangent line and I find the slope of this tangent line, that's the rate of change of this point of the graph. The rate of change is a valuable piece of information for us. It's nice to have. Here's the problem though. That to find the slope of a line, how many points do you need? You need 2. And unfortunately, I have this line that is tangent to my graph at one point, and that's the only point I got. So it's hard for me to find the slope of that line because I need 2 points. And I don't have another point. So, here's what we're going to do. In order to find the slope of this line, here's what we're going to do. We're going to create another point, and then we're going to connect the line that goes through these 2 points, and we're going to use that line as an approximation of my green line. But we're going to create it in a way, and we're going to name it in a way that's going to be helpful to us. The first thing that I'm going to do is I'm going to recognize that if this is x, does everybody see that if this value is x, this point right here is x, comma, f of x, right? That's the green point. That's the point that's on my graph, y is equal to f of x, at x. Now, if I take that point, that place, x, that place x is the same, it's the same place, right? It's the same thing, it's the same place, and instead of, well, in addition to, I should say, using x, I'm going to add a certain distance onto x. And I'm going to call this distance h. Okay, and I'm choosing these just for convenience sake. I can name it anything I want, but I'm naming it h. So if this is x, and this distance is h, is everybody in agreement that this place is x plus h? Does that make sense to you? Sarah, are you on board with that? If this was 2, and this distance was 3, then this place would be 2 plus 3 would be 5, right? It doesn't, I'm not specifying the numbers, but in general, x and then h, I'm at x plus h. And if I go to x plus h, if I go up to my graph, that point is now x plus h, comma, f of x plus h. And I'm going to connect, I now have 2 points. I'm going to connect my original point and the new point. Make this secant line. I know 2 points on that line, on that red line. One of them is x comma f of x. The other is x plus h comma f of x plus h. And I'm going to find the slope of those two points. Remember the slope. What's the slope formula, Max?
y2 minus y1 under x2 minus x.
Perfect. y2 f of x plus h minus y1 f of x over x2
different quotient makes a lot of sense now.
minus x. That's right.
That's a different solution.
I want to recognize that the denominator, the x's cancel. This is gone. This is gone. And I'm left with f of x plus h minus f of x over h. And we've been seeing that over and over and over again recently. That's a difference quotient. That is the formula for the slope between the point x comma f of x and x plus h comma f of x plus h.
Difference quotient slope. All makes sense now.
What do we use the difference quotient for again?
You're looking at it. It's finding the slope of this line. Right? This is when the one I've drawn here is when my h value is 4. Right? I'm counting out 4. 1, 2, 3, 4. For example. And I'm saying, let's use that slope of that red line as the approximation to the slope of the green line. Now, would you say that's a very good approximation? Would you say the red line slope is the same as the green line slope?
No.
It's not even very close. They're both positive, I can say that, but it's not very close. So what I'm going to do is I'm going to say, you know what, let's do the exact same thing, except for let's change our h value from 4 to 3 and move our point.
On what basis can we do that?
Well, I can make the second point anywhere I want. Right? The second. the second point is a made up point just to establish 2 points so that I can evaluate a slope, right? So this isn't a very good evaluation. It's not a very good approximation. So let's make the second point a little closer. Now we're 3 points away instead of 4. I still have the same formula for slope. My slope is still f of x plus h minus f of x over x plus h minus x, which is h. Right? I still have this same formula. It's just that now the evaluation is when my h value is 3 instead of 4. And I want to look at this approximation and say, it's not very good. This one, still not very good. Is this one better? Would you say this is a little closer?
It's a bit closer, but it's still not close.
It's still closer, but it's not really a very good approximation. Let's try it when h is 2 instead of 3. So now I have my h valued 2 units away. And I determine my second point. I still have the same formula for the slope. I've connected these 2 points, and these 2 points make a better approximation than those 2 points.
It's just about.
It's close. I'm not satisfied with using this as my I'm not satisfied with using this as my approximation. Let's go to 1. One's pretty good. But I'm still not satisfied. It's not as good as I can get. Guess what? If I went to an h value of 1/2, I've stopped here. I haven't gone any further than this. If I went to an h value of 1/2, then I would even be better. And then if I went to an h value of 1/4, my point, I have my reference point, and my second point is 1/4 of a unit away. My approximation is better. 1/8, it would be better. 0.1, it would be better. 0.01, it would be better. Guess what the result of this is?
As the limit gets closer to 0.
As the limit of my h value gets closer and closer and closer to 0,
It becomes closer and closer to your x value.
it does become closer to my x value.
No,
This slope becomes closer to
The
the
slope
slope of the green line. In fact, the limit as h goes towards 0
Is the slope of the
is the slope of the green line.
Because that way, when you can't make x edge because then you have the same line twice. So you
Exactly.
make it as close to x as possible.
And it's the limit of, if I get infinitely close, then the limit becomes infinitely close. It becomes the same limit.
So I have would you actually have to draw out like every
No.
You just
This
look
is
at
just for your visualization.
Yeah.
I'm not asking you to draw anything, anything like this. I'm just using this so you can visualize what we're doing. So when I get over to here, and I see, you know what? I can see that the closer this second point is getting, the smaller my h value is getting, that the slope is getting closer and closer and closer. In fact, the limit, the slope of the green line is the limit as h approaches 0 of f of x plus h minus f of x over h. That is the slope of the green line. That difference quotient, the limit of that difference quotient. Okay? Now, let's see how we might be able to use this in a concrete example. So you see, in this problem, I could have worded this in a lot of different ways, but I said, evaluate the slope of f of x equals x squared at the point -2, 4. I might have said evaluate the rate of change of this graph at that point. I could have said find the slope of the tangent line at that point. They're all the same question. But I've drawn for you what it is that they're asking us to do. You see, in the blue graph, that is f of x is equal to x squared. That's a parabola. And the green line, that is the line that is tangent to the blue graph at the point where x is -2. -2, 4. And we want to know what is the slope of the green line. Because the slope of the green line is the rate of change or the slope of the blue graph when x is equal to -2. I know this is true. The slope is equal to f of x plus a, I'm sorry, the limit as h approaches 0, f of x plus h minus f of x over x plus h. Yeah. Now this one is saying, what is the slope when x is equal to -2? Notice it doesn't matter what y is. I can be doing this for any graph. The y value doesn't matter. It matters what the x value is. I'm going to rewrite this as the limit as h approaches 0 of f of -2 plus h minus f of -2 all over h. Why? Because I want to know when x is equal to -2, what is my slope?
No, is that? And then you just.
All right, now I want to evaluate what is f of -2 plus h. Well, let's rewrite the limit part. The limit as h approaches 0. And by the way, I haven't been saying this, and I sometimes forget to say it because it's true every time we do this. But I do want to consider direct substitution. When I put a 0 in for h, I get f of x plus 0, f of x minus f of x, which is 0, over 0. So I get it in determinant form. And when I make my substitution, I get f of -2 minus f of -2 over 0. I still am indeterminate. So I need to go a little bit further. I always forget to say that, but because it happened, that's the way it goes every single time with these, so I don't always say it. But now I can evaluate. Here's my function. This is my function. What is this function evaluated for this point? It's going to be -2 plus h squared minus -2 squared over h. Right, my function is x squared. F of x equals x squared. So when I want to know what is f of -2 plus h, that goes into the squared part. You with me there? If I gave you, you got it? Okay.
So this time we only constructed one line. We haven't constructed.
That's the lines that the red lines that I had constructed were only being used as approximation. The line I'm interested in is only the green line. I don't care about those red.
So we don't actually need to draw another.
No.
It's all up here.
Right, that's right. That's exactly right. green line is the only one that matters to me. So, this becomes the limit as h approaches 0 of 4 minus 4h plus h squared minus 4 all over h. And I see that my 4 and 4 are going to cancel each other out. So this becomes the limit as h approaches 0 of h times negative 4 plus h over h. Does everybody follow that? Now I can reduce the h with the h, and now I can do direct substitution. Put in a 0 for h. What do I get? Negative 4.
Why are we putting a 0?
What?
Why are we putting a 0 for h?
Because h is, yeah, h is, yeah, that's right. It's a direct substitution. But the reason h is approaching 0 is because it's the distance between the 2 points that I'm finding the slope on. So this is negative 4. This is telling me, yeah.
Would you always leave the limit as the 0 when you change it?
Remember, h is the distance between the 2 points. I always want that distance to be approaching 0. Right? You with me? Okay. So just what I'm saying here is that this value, negative 4, I am saying that the slope of the green line is m is equal to negative 4. Also, the blue graph has a rate of change of negative 4 when x is equal to 2. Notice the difference. What's that? Negative 2, thank you. Notice the difference between how I might think about these. For the line, it's the slope. But for the graph, for the curve, it's the slope or the rate of change, but only at one place. This curve, the rate of change is constantly changing. So if I want to refer to it as a number, it has to be a number with respect to a location. It has that number at that location. But the minute I'm on to a new location, I've got a new number. Okay, now the next thing I want to say is that we just found the answer to this question.
Yes. Because we got the value, so we got with the tangent line.
Yeah, that's right. That's exactly right. But supposing I had a problem. Yeah. Supposing I had a problem in which at one stage of the problem I wanted to know what was the rate of change when x was equal to negative 2. And at another point of the problem, I was interested in the rate of change when x is equal to 0. And at another point, I was interested in the rate of change when x is equal to 1. And at another point, I was interested in the rate of change when x is equal to 5. And so on. Do I have to do this every single time I want a new number, a new evaluation? The answer is no. I don't have to do it. I've written that out for you here. If I wanted to know the rate of change when x is negative 2, which we just did, and x is 0, and x is equal to 1, and x is equal to 5, I don't have to do this over and over and over again. In fact, rarely do I do it this way. I almost always do the general form. Let me show you how that's slightly different, the general limit. In general, the limit, the slope is the limit as h approaches 0 of f of x plus h minus f of x over h. That's in general. In this problem, I want you to see that the first thing I did was I put in a -2 for x, because that's the point I was interested in. But supposing I'm interested in general, I'm not going to put anything in for x. I'm going to evaluate it for x. This is going to become this. X plus h squared minus x squared all over h. Not -2 plus h squared, just x plus h squared. And then we can go from there. We've done this before. This is equal to the limit as h approaches 0, x squared plus 2xh plus h squared minus x squared all over h. Cancel my x's, factor out an h. This is equal to the limit as h approaches 0 of h times 2x plus h over h. Reduce the h's. Do my direct substitution for h is equal to 0. So you see the difference between the specific and the general. The specific, I substituted a -2 in for x. So I'm working only at that point where x is -2. Here, I didn't substitute anything in for x. So I'm working at any x point, any x value.
Yeah, you get there you get an expression that you can just solve.
Yes, exactly.
So
So guys, what we just did was your first derivative that you've ever taken. What you just did is the definition of a derivative. In fact, here's the notation, the definition. The notation is, when you're talking about a function f of x, and you want to know what is the derivative of the function, you make a little f and then a little slash between the f and the x. And we read that as f prime of x. That's the derivative of f of x. F prime of x is equal to, by definition, it's equal to the limit as h approaches 0. It's equal to the limit of the difference quotient as h approaches 0. Max.
So we're saying that for f of x equals x squared, the slope is 2x.
Okay, that's it. So let me finish this off, this specific function off by saying this. We have two functions now. We have f of x is equal to x squared, and that function is my function. That function is my function, right? If I'm interested to know, if I want to graph this function, and I want to know points on it, I choose my x's, and I evaluate, and that gives me my y value. And I can plot those points. I can do that all day. The function gives me a way to generate y values, output values. But I can also take the derivative of this function, which I just did, and found that the derivative of this function is f prime of x is equal to 2x.
2x is h.
No, h is 0.
H is always 0, so it doesn't matter.
So the function is f of x equals x squared. The derivative of the function is f prime of x is equal to 2x. Now, the function gives me a way to generate y values. The derivative gives me a way to generate rates of change.
But will that 2x work for every single point in our graph? Is that